Now let's give some examples of function compositions. Example number 1. We start with the following definition of the function f, which maps all real numbers into real numbers, and for every x is mapped into f of x, which is x plus 1. And our second function g will map all reals positive or 0 into reals, and every y is mapped into g of y, and the function g of y is an abbreviation for the square root of y. Now, we want to make the compositions and get the domains for both compositions. So let's start with the first one. So the composition of f of g, you see, first you act with g on the independent variable, but the independent variable of g is y, so this thing must act on y, and this number is, by definition, f of g of y. In turn, what is the number g of y? Well, g of y is the square root of y. And so where this symbol is, let's replace it by its abbreviation. So f of the square root of y. In turn, what we find is the square root of y plus 1. So where was x, now is the number, this form here. Now this is the first decomposition. Now let's get the domain of this function. What is the domain? The domain of this function of f of g is what? Well, it's all those in the inputs, is all those inputs in g, so all y's belonging into the domain of g, as long as their images, so g of y, belongs into the domain of f. Can you see? Now, specifically, we know what is this thing and this thing, because we have just defined it, okay? So, the domain here is all the reals, positive or 0. So, here we find all reals, positive or 0. And the domain of f, it's here, it's all reals. So this is all reals. And now we have a set to compute. Specifically, this set is given as follows. It's all y's belonging to positives or 0, as long as the square root of y lives in R. If you look carefully, for every positive y, including 0, well, the square root of it is always a real number. And as a consequence, there is no restriction, so all y's, in positive or 0, enter in this set. This statement here, the element U test, does not pose any restriction on what y's are we going to select. So as a consequence, this set here is all positive reals, including 0. Now let's look at the second composition, meaning g of f. What is g of f? G of f, well, first f must act on its input, but we just define the inputs as being x here. Can you see? Here. So first f acts on x, and then g acts on this number. Okay? So as a consequence, now what we know what the f of x is, it's here. It's an abbreviation for x plus 1 for this number. So we have g of x plus 1. But what is g of x plus 1? Well, it's a square root. Square root of x plus 1. The domain of g of f is what? Well, it must be all those x's in the domain of f. So all those x's in the domain of f, as long as this thing here, f of x, is in the domain of g. Specifically, we know the following. We know that f of x is x plus 1, and we know that the domain of this thing is R, and the domain of G is all positives including 0. To compute this set, now let's rewrite it in a more manageable way. So, we say that it's all x belonging to R, as long as x plus 1 belongs to the domain of G, its x plus 1 must be greater or equal to 0. Now, let's rephrase this thing, because to say that x plus 1 is larger or equal to 0 is the same thing as saying that x is larger or equal to 1. So, what we are seeking, in fact, is all those reals as long as they are larger than 1. So, in turn, this set is from 1 up to plus infinity. And this is the domain of this composition. A key takeaway from this example is that usually when we define the domain of a composite function, the element 2 test that we find here is usually some equation or some inequality that we must solve. Here, this statement is equivalent to this statement, which is in turn equivalent to this statement. But I think you agree that this statement makes it absolutely obvious what are the x's that enter in this set. So usually our goal is, when we define this thing, is to rewrite the element 2 test, to simplify it, so as to make it clear what are the elements here that enter in the set. Now, let's see another example.